All right, so the rational and Jordan canonical forms. We began by asking a few lectures back, when and how could you decide whether two matrices were similar? Actually, I asked a slightly different question. I asked when are two linear transformations the same, but then we learned that that was really the same question as when are two matrices similar, right? And minimal polynomials ain't going to cut it. Like, these two matrices have the same minimal polynomial, but in fact they're not similar because they have different traces. And we know that similar matrices have the same trace. And characteristic polynomial won't cut it because these have the same characteristic polynomial. All right, but they're not similar. And the questions of similarity are very, very nicely settled by this elementary divisor theorem, which we're not going to prove, but we're going to try to understand it, okay? And here it is. Well, this isn't the theorem yet. Here's something we need to understand the theorem. A t-invariant subspace is called cyclic relative to t. If v1's not 0 and there exists a vector v1 such that v1 is the span of v1, tv1, t squared v1, tk v1 for some k. Now, so here's a lemma. So that's the notion of a cyclic subspace. Basically, you can, if that's the case, we can say v1 is equal to the notation, you guys, is that this, I'll fit it in here. We use this notation. It's like brackets v1. It's built from v1. v1 builds that thing right there, that cyclic subspace. All right, here's the deal. Subspace v1 of v is cyclic relative to t if and only if for some vector v1, non-zero vector, every vector in v1 can be expressed in the form f of t times v1 for some polynomial. All right. So fine. If v1 is cyclic, then there exists alpha naught through alpha k such that v is equal to, you know, this polynomial, right, and t. But you could rewrite that. That's polynomial, and that's f of t times v1 for the obvious. F of x equals to, well, I've written f of t is this, right? But you could see f of x would be alpha naught plus alpha 1x plus plus alpha kx to the k, right? Oh, right there. All right. So their cyclic implies that. You notice that v was arbitrary. Conversely, if there exists a v1 for which, you know, there exists an f of x, for which every vector there exists some polynomial such that v is equal to, you know, f of t times v1, evaluated in v1, then that means v is in the span of these guys, all right, which is in the span of these, and k has to be, I mean, k can't be infinite here, it has to be finite, so it follows that v1 is cyclic then from that condition. All right, well, that's the start of it. Definition. Well, I just told you the cyclic subspace generated by v is denoted like that. But here's the actual here's the we say generated by v. What do we mean by that? We mean you take arbitrary polynomials in the field, you evaluate them at t, right? That gives you basically arbitrary transformations built from t, well, polynomials of t again, that acting on v. All right. Well, all such things forms v1. That's how we generate. By the way, you can easily prove that if this is how you define v1, it's closed under addition and scalar multiplication. Lemma. Let v be in v non-zero, then there exists a non-zero polynomial with leading coefficient 1, all right? In other words, it's a monic polynomial. And this m sub v of x is equal to x to the d minus alpha to the d minus 1, x to the d minus 1 minus alpha naught, such that m sub v of t acting on v equals to 0. And for each f of x in the polynomials, each polynomial f of x, if you have evaluation on t acting on v equals 0, well, that implies that the mv of x divides f of x. this has a name. This mv of x is called the order. This is called the order of v with respect to t. Don't usually say that everything is with respect to t. We don't usually say with respect to t, but it should be understood everything here is with respect to t. Here's the proof of the lemma. So we have that this span is a subspace, right? That means there exists a D for which this is linearly independent. And yet, if you go one more step, it's linearly dependent, right? Hence, TdV is in the span of these guys, which means that there exists alpha naught through alpha d minus 1 in the field for which TD is this linear combination. All right. And then you just define, you construct mv of x to be that polynomial, replace the t's with x's. Then, well, by construction, mv of t is 0, right? And also, if you have f of x that annihilates, when you plug in t, you annihilate v, you can use the division algorithm to get the claim of the lemma. Let's see here how. F of x is equal to m of v of x times quotient plus the remainder. Either the remainder is 0 or the remainder has degree smaller than mv of x. All right. Notice that ft acting on v, if this is equal to 0, right? Then, well, this is equal to 0, right? Because mv of t is, we already showed that. And so if this is 0, that's automatically 0. That forces rt of v to be 0. All right. Which implies then that r of x is equal to 0 since r of x is not equal to 0. Right? Either r of x is equal to 0. I mean, so if it's r of x is equal to 0, we're done. If r of x is not equal to 0, then we've got something to worry about. But so anyway, this implies that the RT of RT of v is equal to 0 is a linear dependence among powers of t, the before TD. Basically, if it were the case that RT of v was equal to 0, right? And if r of x was not 0, then this would contradict the minimality of the d that I constructed m sub v, the order of v with, okay? So in order to not contradict the minimality of the d, which was formed from linear independence up here, this part of it, then we have to have that r of x is 0. But if r of x is 0, that implies that the order of v divides f of x as the lemma wants. All right. So that justifies the following definition. If we have v in the vector space v naught 0, the unique polynomial mv of x, for which mv of x is monic and mvt is equal to 0, such that whenever f of x is a polynomial and when evaluated at t annihilates v, implies that the order of mv of x divides f of x. It's kind of a complicated definition, but it is what it is, all right? Well, that's called the order of v. That is, mv of x is the order of v. In other words, q of x is the order of v if it's the monic polynomial of least degree for which qt acting on v is 0. Notice that the linear transformation t is fixed throughout this discussion, and the vector space v is a finite dimension over a field f. Consider the following. If qt of v was equal to 0, then mv of x divides q of x, right? If q of x is minimal degree amongst the f of x such that ft of v is equal to 0, that implies that the degree of mv of x is equal to the degree of q of x. But q of x is equal to alpha times mv of x implies that q of x is equal to mv of x since they're both monic, and that means that the coefficient by which they're related has to be 1. So here's a lemma. If the cyclic subspace generated by v is non-zero, and we consider T restricted to the cyclic subspace generated by V as a mapping from cyclic bracket v to bracket v. The order, all right, the order mv of x is, in fact, the minimal polynomial of the restriction of t to the cyclic subspace. Well, that is very nice. Wondering when the m's were going to get connected, right? All right, so here's the proof. Notice for v not equal to 0, f of x has ft of v equal to 0. If and only if the f restricted to t of v is equal to 0. This follows from the fact that v is the span of these guys, right? Just to be careful, let's assume that this is 0. What's that say? Well, that says that alpha naught v plus alpha 1 tv plus da 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 plus alpha k t k v is equal to 0, right? But that's true if and only if alpha naught plus alpha 1 t restricted to v, alpha 2 t restricted to v squared. I mean, I can just rewrite this in terms of the restriction of the sum of these, operators restricted to the cyclic subspace acting on v equal to 0. Or in other words, f of t restricted to the cyclic subspace v equal to 0. Sorry. Suppose q of x is the minimal polynomial of t restricted, right? Then we have mvt is equal to 0 on the cyclic subspace, right? So we'll find that q of x divides mv of x. But on the other hand, qt of v equals to 0 implies that mv of x divides q of x. Aha, so we have, they're both, q divides mv and mv divides q. That means that they must be related by a unit. But what's the deal? Well, m was monic, right? And q was also monic, because we assume it's minimal polynomial. Well, he has a theorem stated with an ambiguities, like it has to be, they're unique up to a unit. If you were to say q is monic, it would imply unique, but if q doesn't have to be monic, then we have the desired result, which is that mv is the same as the minimal polynomial up to a unit on the cyclic subspace if you look at the restriction. All right. So if m of x is the minimal polynomial of t on v, then for each v not equal to 0 on v, we have mv of x divides m of x. Well, this is very useful. I've asked you guys to find the orders of I think I asked you to find the order of various eigenvectors different places, right? And so if you think about this is really huge, because it means if you know the minimal polynomial, the only thing you have to look at to determine what orders are actually the right order are just factors, right? Because it has to be, it has to divide m of x, right? This is very, it means you can basically just check some things. You don't have to do an arbitrary calculation. You can just check the factors and see which one it is. And this lemma pretty much pins down the order in terms of this kind of idea. Proof. Since minimal polynomial of t is equal to 0 on v, that in particular implies that mt of v is equal to 0 for a particular non-zero vector v. And so that then implies that mv of x, the order of v, has to divide m of x by lemma 25.4. Yay! Again, as I was just saying, if you know m of x in factored form, then this lemma puts rather severe restrictions on possible orders for v, or in turn, this possible structure of a cyclic subspace. All right. Again, I think to really understand that properly, we must understand the chains, all right, which I have not exposited in these notes. That brings us to the elementary divisor theorem. Here it is. V be a finite dimensional vector space over V, T a linear transformation on a non-zero space. There exist non-zero vectors, V1 through Vr, whose orders are prime powers, polynomials, P1x to the E1, P2x to the E2, Prx to the Er, and are such that V is formed from the direct sum of cyclic subspaces, V1, V2, circle plus dot 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 circle plus Vr, the direct sum. And the number of summands R is uniquely determined, as are the orders, P1 x to the E1, PR x to the ER of the vectors V1 through VR up to rearrangement. All right, the proof is not something we're going to go over in this course probably. It's in section 29 of Curtis. He uses things like dual spaces, and I think when I'm talking about chains, I think the chain materials over there, I don't know. Again, I'm struggling with how to better communicate this to you guys, and I'm working on it. Let's see, anyway, so moving on here. I will give a rather complete proof in the real case, because the real Jordan form basically takes the role of the rational canonical form, which is what we're almost to here. All right. Rational canonical form is pretty much a corollary to this elementary divisor theorem, just choice of basis and junk. But this much I should tell you: the set of prime polynomials to these powers, this is called the set of elementary divisors of T. That essentially settles the classification question of when are two matrices similar. Basically what we're going to learn is they're similar if they have the same set of elementary divisors. Example, if T has elementary divisors, x minus 1, x plus 1, x plus 1, and x squared plus 1 over the reals, that means that V is the direct sum of this, and this, where V1 has order x minus 1. Oh, I'm not supposed to tell you that yet, am I? Oh well. V2 has order x plus 1, V3 has order x plus 1, and V4 through 4 has order x squared plus 1. And it will follow that if you use the basis V1, V2, V3, V4, all right, that's, I don't know why I've got the, I think just that would be enough. I don't know why I've got T of V4 there. That's nonsense. I don't know. Oh, wait a minute. Oh, yeah, T of V4. Sorry. Beware of the sleepier me arguing with the less sleepier me. All right, anyway, going on. So this would be a 5-dimensional space. Yeah, 5 by 5, okay. And so, yeah, it turns out that the matrix with respect to this set of, like, cyclically generated subspaces, only the fourth one is really interesting in some sense. It gives you this matrix. This is an example of what's called the rational canonical form. I'm jumping ahead a little bit. Here's the lemma. Again, the elementary divisor theorem in and of itself not that awesome. Well, I mean, it is awesome, fine. It's full of awesomeness. I'll admit it, but this is actually more concrete and useful for us. If we have p of x equal to x to the d minus alpha to the d minus 1, x to the d minus 1, like so, this polynomial, and if that's prime, then the cyclic subspace, all right, and if V is a cyclic subspace of which V has order p of x, in other words, envision this being the order of V, some non-zero thing. Then if you take the basis t, tv, t squared v, t to the d minus 1v, if that's a basis, then the matrix for T restricted to the cyclic subspace has the following rather simple form. This is a so-called companion matrix. You got ones down the subdiagonal, all right, like that. And then in the last column, you have the alpha naught, alpha 1, alpha d minus 1, like that. Now, in his formulation of the companion matrix, there are no minuses here. That's because he put some minuses up here. Other books you look at, they might have pluses up here, then they'll have minuses over here. Somewhere you have to face the signs, all right? This is the companion matrix of p of x. The proof is actually kind of fun. Really, again, it's just going back to, do you understand basis and coordinates? It's all about basis and coordinates, folks. So we're choosing the basis beta to be f1, f2, fd, where fj is equal to tj minus 1 of v for 2 to d, and f1 is the first thing in the basis is just v. So to get started, if you look at T restricted to the cyclic subspace acting on f1, well, that's just T of v, which is, by the way, f2. So there you go. The first column, It just has 0, 1, 0, 0, 0, 0, like that, all right? Then you look at the jth one. So, okay, so that's tj minus 1 v, right? But that's tj v, which is, by the way, fj plus 1. That's going to hold for j equals to 1 all the way to d minus 1. That gives us the first d minus 1 columns as just being like one below the column. Like there's this first column has a non-zero thing in the second row. The second column, non-zero in the third row. The third column, non-zero in the fourth row, and so forth and so on. All the way right up until you get to the last one. Now, if you evaluate an FD, well, then we've got t of td minus 1, which is tdv, but hey, that is alpha naught v plus dot, 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 right? Because the order of p of x, excuse me, was given to that. So, like, if I take t of d minus this, I get 0, right? This follows from the order, the fact that p of t should be, if I say this, intuitively td of v is this, right? So I'm trying to think how can I explain that? It's because we said the v has order p of x. That means pt acting on v is 0, and from that follows this equality, okay? But that is exactly the interesting last column, all right? Remark, be careful not to assume that pt of v is equal to 0 when we're looking at p of x to the e for e greater than 1 being the order of v. I will tell you, that caused me a considerable confusion. All right, so here's an example. P of x squared minus 2 is prime over q. Since x squared plus 1 is equal to x squared, I think that's just I don't really follow that up. I just wrote that there. I just like left it hanging. Okay, sorry about that. Since x squared plus 1, x squared minus 0x minus 1 is, we can see that you have alpha not equal to minus 1, alpha 1 equal to 0. And so you obtain the companion matrix 0. There's just 1 on the subdiagonal, rather boring here. And that's minus 1 and then 0. So there you go, that's the companion matrix. And he says it's a sub x squared plus 1 because this is the companion matrix for that polynomial, which is, it's a nice notation. And then you have to face the music. The music is the prime power case. All right, prime power case. All right. So if you have p of x is equal to this, and v is a cyclic subspace where v has order p of x to the e, for some e in the natural. Really, we're thinking e be equal 2, 3, 4, whatever. Then the matrix of t restricted to the cyclic subspace with respect to the basis beta. All right, now notice carefully this basis is constructed in a rather, specific way. We start out with p of t to the e minus 1, all right, v, and then you operate on t, and then t, and then t, and then t, all the way up to td minus 1. And then he drops the power of p to the t down 1, and he acts on v, and then he lets the t act on that, and then again, and then again, and again. Eventually, he gets to p of t e minus 3 on v, which I have not written. And this continues. Eventually, you exhaust all the powers of p to the t until you just got down to v. And then you go tv, t to the d minus 1v. And there you go. That's your glorious basis in this case. What's the dimension? E times d, I believe. All right. Well, the claim then is that the companion, quote-unquote, let's say companion matrix, it's not quote-unquote, it is a companion matrix, all right? Companion matrix in the, let's say, syntax and conventions of Curtis, all right? Looks like this. So these A's are the companion matrices we talked about before for P of X, and B is a rather boring a 0, 0, 0, 0, 1, and the rest zeros. All right. Here's proof. So to start with, most cases of I, all you got to do is just go, okay, so tj, that is just tj plus 1, that. But that's just gi goes to gi plus 1, and that holds for most cases of I, except for the cases where I is a multiple of d. In other words, that's exactly what we had in A. That was the case where A was just the one below. It's just the subdiagonal ones there, all right? The interesting case, of course, is the, the other case. So, like, if we look at J times D, in other words, one of the multiples of D, then we'd have T of TD minus 1, P of T, TE minus JV. But that would be TD acting on PTE minus JV, all right? And that we can commute these because they commute because they're both made from T. So I've got this times TdV. And then I must be careful, you see, because what I have is that I have P of x is equal to this, right? So T to the D is in fact equal to P to the T plus alpha to the D minus 1, T to the D minus 1, and so forth and so on. So I can trade this T to the D for all of this stuff, plus P of T to the what? And still have this E to the J minus 1. Now the plus 1 comes because there's also another P of T here, right? All x on V. Now this calculation makes sense for j equals to 2, 3, e. Now if you look at that, what you have here is, on the one hand, you've got this, this is j minus 1 times d, this is j minus 1 times d plus 1, all the way down to jd. That's exactly the, those are the, so if you look at like the dth column, well, 2dth column here, you're picking up the coefficients that are coming from the order, these coefficients down there. Now hopefully we're going to see where the 1 came from in the D. Well, it's coming from this guy, which came from this, which was this extra P of T here. All right, so therefore we have let's see here. Now if I look at this is a specific case. If I look at the dth column, all right, that's special because there's no B. There was no B in that case. There was just the A. So this explains like 2D, 3D, 4D, 5D, all the way out to ED. This is for D. So this is the dth basis thing. I let it act on by T, TD, P to the T, E minus 1V. Commute them, and then I trade my TD V for, oh man, all this stuff. The thing that's there's a missing. I said there's not a missing. Why do I have it there? I'm sorry. And there should be, of course, plus plus the P of T to the E minus 1 times P of T, right? Why is that? It doesn't matter that I don't have that P of T. Times P to the E minus 1 T acting on V. Well, this, of course, is P of T to the E acting on V, which is by definition 0, right? Because that's the order. I was originally missing that. Well, anyway, who cares what I was originally doing? Let me show you how it works. So here's the 2D case. So you get this is equal to that, is equal to that, is equal to that, plus this piece equal to this, plus this piece, but that's G1. That explains this one, the 1 here, and then the alpha's down here, and then the zeros below it. And so there it is. That's why there's a companion matrix, why it looks like it does. Here's an example. Example C of page 222, a good example. If you look at x squared plus 1 over q, we have the basis beta p of t, v, t p of t, v, and then t of v if I follow his lead. And so we'll obtain this matrix since the A is 0, minus 1, 1, 0. That's the companion matrix of x squared plus 1. And here I just walk you through the calculation. So like if I look at p of t is x squared plus 1, right? So like t of x squared, t of t squared plus 1v would be t times t squared plus 1, right? But that would be t times p of t v, and well, that's exactly 2. So that's G2, which means that column 1 is just 0, 1, 0, 0. Column 2, right, we get to t acting on t p of tv. I do that, I commute them, I add 0 suspiciously for some reason, and that gives me, well, the reason I have p of t times p of t, but p of t squared is 0, right? So this times that drops out, and I'm just left with a minus 1. In other words, I get t squared plus 1. We'll pull the minus out, I get minus p of tv, but that's G1. And so that's where the minus 1 comes from here. And then finally the interesting one, column 4, I get t of tv, right, because tv was that one, the fourth thing, but that's t squared, and I add 0 again because that's what I like to do. And so that gives me t squared plus 1, which gives me p of t, v, and then minus v, but hey, that's exactly G1, and that's exactly G3, and that's why we get this 1, 0, minus 1, 0, which is what's, we got this A, and then B, and then 0 here in the general pattern. Oh, I'm sorry, I was talking off script, off the page here. Let me go through it again. So t of tv, this is G4, t squared plus 1, minus 1, so I just added 0, right? And so the t squared plus 1 is the p of t. The minus gives me the minus, and well, this is G1, and that's G3, so that's why the fourth column I get 1, 0, minus 1, 0. Of course, if you really believe the theorem I just proved, I don't have to go through these calculations, right? I can just write this down. I can just write this down because I understand the theorem, and you're welcome to do that, okay? I'm just trying to, if you still have lingering doubt, personally, I had to do this in order to like free my mind of something I was stuck on in the proof. So anyway, finally. So you can also talk about elementary divisors of a matrix. They're just the elementary divisors of the linear transformation, which is induced by said matrix. And the so-called rational canonical form of a linear transformation is the companion matrix for the transformation, where you're forming the basis by concatenating the basis we just constructed for the companion matrix, basically. So you take the elementary divisors of T, and you find the vectors which take those as their orders, and you make the basis with respect to those vectors, which are the generators of the cyclic subspaces. And there it is. That's the so-called rational canonical form, which has blocks which are companion matrices, all right? Likewise, for matrix A, the rational canonical form of A is the rational canonical form of the induced transformation. Just to give you an example or two, the rational canonical form is unique up to reordering, and I lost my paper. Where'd my paper go? It's unique up to reordering. So basically the set of elementary divisors completely governs the structure of the rational canonical form. So here's just an example. This is a prime polynomial, and that's a prime polynomial. I happen to know that because I looked in page 310 of Dummett and Foote. It's maybe not obvious that these are prime, but they are. I mean, hey, for that matter, folks, you could form a companion matrix for a polynomial which wasn't prime. There are good reasons to do such from the theory of differential equations. I have a problem in your, I think, quiz about that. Don't be scared of that problem. It's not that hard. So anyway, if you look at the companion matrix, you get ones in the subdiagonal, ones in the subdiagonal, and then the coefficients with the proper signs injected, put in up here in the last column of the block. So I get like -5, -10. There's no square and there's no cube. This one I get -2, -4, -6, and -4. These ants crawling on me weirded me out. I'm not crazy. We have ants in our house. Yeah, there you go. That's the companion matrix if you're trying to reproduce these if these are your prime powers. If these are your elementary divisors. That's the rational canonical form. Finally, well, almost finally, we're nearing the end here. Two n by n matrices are similar if they have the same rational canonical forms. Here's the proof. If there exists basis beta and gamma for which LA beta beta is C and LB gamma gamma is C, then that means there exists PQ invertible such that P inverse AP is C and Q inverse BQ is C. So you can set C equal to C, you see? Oh, sorry about that. Not so sorry though. I could have stopped the recording and started again, but I'm not going to. Anyway, I digress. So you solve this, the usual stuff for B, and then you've got B is similar to A because, hey, that's exactly PQ inverse A, PQ inverse, which shows that A and B are similar. And there you have it. Same rational canonical form, similar matrices. The rational canonical form is unique up to rearrangement of the blocks. That's like pretty much immediate from the elementary divisor theorem, right? The elementary divisors uniquely determine the companion matrices, and so those are the blocks. Worst thing you could do would be reorder them. So, there it is. Not much to say there, really. It's already obvious from the construction. Now, the Jordan normal form, which I'll spend a lot of time talking about when we get back from this break we're currently taking. Well, that's a rational canonical form in the case that all the characteristic roots, the eigenvalues, actually belong to the field. In this case, the elementary divisor has the form x minus alpha to the e, and the companion matrices have the form like this. So those b's are just, they collapse down to just 1 by 1 matrices. And the a's are actually they're just 1 by 1 matrices with an alpha in them. It's very silly, but that's a Jordan form. All right, alpha, the characteristic value down the diagonal, and 1's on the super diagonal. Here's some examples and some indications of things to come. All right. So example 1. If I had this set of elementary divisors, x minus I cubed, x minus I, x minus 3, x minus 3, x minus 3 squared, x minus 3, all right? This would give me this block. That would give me this 1 by 1 block. That would give me a 2 by 2 block. These are all Jordan blocks. And this would give me a 1 by 1 block like that. There are 4 eigenvectors here corresponding to this, this, and this. In fact, but these first 3 actually come in a chain. What that means, if you want me to be more precise about that, is if I take j minus I times E3, you can calculate that you'll get E2, where E1, I'm talking about E3 and E2 being standard basis, okay? So in other words, if you multiply E3 on the third column, you get back E2. Oh, sorry, not the third. You calculate this, you get E2. If I take j minus I E2, I get E1. If I take j minus I times e1, I get 0. That's not, you can see that even. If I subtract I times I get zeros here. So if I take e1 times a matrix which has column 1, 0, I get 0 again, right? In other words, e1 is an eigenvector. e2 is kind of sort of like an eigenvector, but it's not an eigenvector, and likewise for e3. In fact, e2 and e3 are what are called generalized eigenvectors. And e1, e2, e3 is a chain of generalized eigenvectors belonging to eigenvalue I. Okay, again, more on that after break. Likewise, you can see that j minus I e4 is equal to 0, so I is an this e4 is an eigenvector with eigenvalue I. Oh no, Mr. Ant. And then likewise e7. So j minus 3I times e7 gives me 0. So e7 is an eigenvector. If you look at e5 and e6, there's another chain there. Like j minus 3I times e6 gives me e5. J minus 3I times e5 gives me 0. That makes these a chain of generalized eigenvectors belonging to eigenvalue 3. The length of the chain is 2. I will tell you this. The minimal polynomial for this thing is actually x minus I cubed times x minus 3 squared. What you do... Ants. Stupid ants. Sorry, distracted by the ants again. Man, what am I going to do about these ants? So annoying. Sorry, distracted. You look for the largest Jordan block for each of the eigenvalues, and that's what you keep. So like here are the 3x3 wins, here are the 2x2 wins, and that's why I have that minimal polynomial. You can draw a picture, a so-called tableau. This is from Demano and Little. We used that last year, and he draws pictures like this. He doesn't put the eyes in there, but I put them in there for your help. So this is kind of a picture of what's going on with the eigenvalue I. This is kind of a picture of what's going on with the eigenvalue 3. You can see that you've got like 4 total dimensions attached to the I and 3 to the 3, but you got 2 eigenvectors for each of them. All right, and there's a chain of length 3, there's a chain of length 2. Just kind of a pictorial representation of what's going on. Let me show you another one. So here we have J, excuse me, this Jordan, I actually give you a Jordan, man, stupid voice, Jordan block decomposition. Here would be the tableau for it. I got 1, 2, 3 eigenvectors, 1 generalized eigenvector order 2 attached to this one in a chain. So I've got 1 chain of length 2, 3 eigenvectors with eigenvalue 2, and then I got this 3x3 block with eigenvalue 3. So I have 1 eigenvector, and then it's a chain of length 3. In this case, the minimal polynomial would be x minus 2 squared times x minus 3 squared, because that's the biggest. And if you go back and look at my earlier claims about minimal polynomials, you'll see that it's consistent with what I'm describing here. You look for the largest block for each eigenvalue, and you take the product of those. That's the minimal polynomial. So anyway, guys, that's all I got for you now. I hope you enjoy it. Thanks.